Hello, good evening all. Uh, I think more people might join. We might wait. We can wait for like a couple of minutes. So in the meantime, I'll just go through. There were some audio issues in the previous video, so I thought maybe I'll go through a couple of problems from the last week.
Okay.
So this was a problem where we have a mixture of some chemical species, where the overall mixture is defined by the weighted average of enthalpy of each and every individual species, and our objective is to determine the conservative equation for the overall mixture. So for enthalpy, we have the following relation where rho times dH dt is essentially divergence of K by C times grad H plus you have some source term. Now for a steady state, you have this term essentially going to 0. Now we already have H as sigma ml HL. So if you were to substitute the equation back in the original in equation number 1, we essentially get del dot the summation can be taken out. Plus S equal to 0. If we compare this with our general scalar transport equation, we have phi as H and gamma as K by C. K is your thermal conductivity and C is your volume average specific heat. The only thing we are left out is how do we determine the source term. In order to obtain the source term, we need to have the equation for each and every individual species. So for a given species, we have the for at steady state, we have del dot, let gamma L be the diffusion coefficient for that particular species, ml times HL plus SL. SL is the heat generation term, enthalpy generation term for that particular species, equal to 0. So if we consider this as equation 3, this is our equation 4. Now if you do a summation for all the species on equation 4, what we essentially get is summation of plus summation over all the enthalpy generation terms is essentially, I'm just calling it SH. So this equal to 0. This is my equation number 5. So now if you see equation 3, just do some slight rearrangement. So essentially we add and subtract a gamma L term plus S equals 0. This is my equation number 6. Now if you substitute equation number 5 in 6, what we get is this term over here is essentially minus SH plus S equal to 0. So we have the source term as SH, where SH is the summation of all the individual generation terms for all the species, and we also have divergence of gamma L minus K by C times grad ml times HL. So this is how the overall generation of enthalpy is related to the species individual generation enthalpies. So essentially the first term is the generation enthalpy for that particular species, and this is essentially because of the non-homogeneity of the species distribution inside our volume. So this is one question, and then we have we discussed this another question where we have how do we determine whether one equation is coupled with other equation or not. So when you consider the equation shown over here, so for an incompressible flow, del dot u equal to 0. So this term goes to 0 and this particular term goes to 0. So mass conservation essentially gives you del dot u equal to 0. So here you have for a 3D case, you essentially have u, v, w as unknowns. So these are my, so let me write the unknowns and the equations. So if you just consider the mass conservation, we just have divergence of velocity as 0. We have 3 variables, 3 unknowns and only 1 equation. Now when we come to momentum equation, here again we have u, v, w, like we have 3 equations, each for x, y and z component of velocities, and our pressure itself is an unknown. The tau over here, if you use the closure using Newton's, for a Newtonian fluid, tau is again related to your material property, and it also depends on your velocity profile. So assume that we know the mu, then this tau is essentially a function of velocities, so it's not an unknown. So we have 4 unknowns here, u, v, w and pressure, and only 3 equations. Now when we go to temperature, here we are having the temperature, and since it is an incompressible flow, the pressure term goes off. So we are left with the temperature and 3 velocities as unknowns, and we have 1 equation. So now if you see for mass and momentum conservation, if I take both the equations together, I have 4 unknowns and 4 equations. So I can solve them for an incompressible flow and then get a values of for all the 3 velocity components and 1 pressure value. Once I know these values, then I can in the energy equation, out of the 4 unknowns, I will be knowing all the 3 velocity components. So I will be left with only 1 unknown, that is the temperature. So I can solve this 1 equation to get the temperature. The same is a case for any general scalar equation. Now this is a case for an incompressible flow. Now if you have a compressible flow, then the effects are like the first equation itself will have another unknown, density will be another unknown that will be varying as a function of your velocity. So the equation get coupled with energy equation as well, but we are anyway not dealing with that. Now in this week's of lectures, majority of discussions are focused on how we apply finite volume method, and then there were discussions on what is accuracy, what is consistency, and how do you see for convergence, and then the professor also discusses about a diffusion equation. So we'll be going through some problems on that, and then we'll also see how to implement them for, like how to implement it in a code for a 1D diffusion equation. We'll take some examples on that. So the first question here is, say you have a differential equation ut equal to b times uxx, and if I'm giving you the discretization way as follows. So the subscript is essentially your what I'm trying to do here is in finite difference way, where your entire domain is first split. This is across space dimension, say x, and again you also have a time dimension. So basically the subscript denotes the space dimension and superscript is for the time. So for ut is essentially your del u del t is given by this expression. This is your central difference formulation, and uxx is given by this particular expression. If you are trying to use this particular differencing scheme, how would you go and find about the accuracy of this scheme, and how would you know about the consistency? So maybe let us start, like what do you mean by accuracy is essentially if you try to, okay, maybe I can just hear from you. So how do you go about solving this? So I just want to know, like if I tell you this as the differencing scheme, how will you find the accuracy and consistency of this scheme?
Yeah, so I think you use, can you hear me by the way?
Sorry?
Can you hear me? Because
yeah, I can hear you.
Just reload because yeah, it's clear. Yeah, my network has some issues anyways.
Yeah.
So you take this UT, you use Taylor series expansion from finite difference method,
Okay.
and so you can take UT as t plus 2 I n plus 1 is
UTS.
equal to n. Let us take u at n plus 1. Say that you want to compute value at u at n plus 1.
Okay.
Which is t plus delta t equal to u at n plus du by dt times delta t, right? And plus d square u by dt square times delta t square.
Okay, just
or
take
n
it.
plus-
You
Huh.
just
So
take a
here
Taylor
we are trying
expansion.
to get du by dt, right?
Yes.
So we have ui at n plus 1 minus u of u at n. If you just move this ui at n to the other side, and you can get du by dt. So you essentially have an error of delta t square. You're leaving, or you understand what I'm trying to say here?
Yeah. Okay.
So you're trying
So
to get du by dt,
okay, I got you.
and so you divide by delta t,
Okay.
and you essentially are left with order of delta t times d square u by dou t square terms. You du by dt equal to
Okay.
so we are left with this. So we are left with this. It's hard to explain from here because you are
Yeah,
writing.
yeah, I understood.
Yeah.
So,
Yeah.
like, just for the benefit of others, I'm just writing whatever you're saying.
Yeah. That's good. Yeah. Thank you. Oh,
So,
that's too late, huh?
yeah, I mean, it just goes off to
Yeah.
delta t square, so you need to write more expressions.
So we're trying to find du by dt, right? Because our expression is so we are the last equal to the second term. We're
Yes.
trying to get that term out. So that is equal to u of I at n minus 1 or u of I n minus
So,
1 plus 1, right? I'm writing like this.
yeah, essentially you want to subtract 1 and 2, right? It's central difference.
Central difference. All right, yeah.
So, essentially the first term goes off.
And you're left
Like
with-
basically even term goes off.
Yeah.
So, you're left with
You're left with delta t square terms.
2 delta t del u del t, and then you will be left with 2 times delta t
squared by 3 factorial. 2 times,
and
yeah.
u t. So essentially, if you take ui n plus 1 minus ui n minus 1 plus 2 times delta t will give you del u del t plus delta t square times del cube u del t cube. So this essentially is what you are saying as order of delta t square.
Yeah, so the error
So-
of our accuracy in time, not in space.
Yeah,
That's
in time
important.
is this.
So in time is order of delta t square. So if your delta t is reduced by half, then your error would be reduced by square of that.
So 1/4.
If it is in time.
Okay.
Exactly. So if you get the space,
So
like same
let's take the
space.
space equation. Space equation is kind of having both time and space. So this is expression for
That's what
space.
it's surprising how you have this ui in minus 1 and I.
Yeah, I can
don't know.
I can discretize in whatever way I want, right? Like this is just a scheme.
That's true.
I'm proposing a
Yes,
scheme. So we just want to analyze how
yeah.
you go with it. That's it. So maybe you can try this out yourself and see what is the order of this equation or accuracy of
No,
this.
it's not clear for me, like how are you getting that ui n minus 1 term in the first place? So, anyways.
This one.
So, yeah, so the ui n minus 1, there is this term, right?
Yes.
So, now you raised his hand. I'll let him
Yeah.
speak then.
Someone raised your hand. Yeah, Nagaraju. Yeah, yours.
Yeah, Durga Prasad, in fact, analysis of the accuracy consistency means, these both terms which are depends upon the space and time, right?
Yes.
So whenever we reduce the delta x,
Yes.
so we will get the more consistency, in fact.
Okay, we'll get to consistency later. Like initially we were currently discussing just on accuracy. We'll come to consistency again.
Okay.
Like first we'll discuss accuracy and then we'll go to consistency.
Okay, sure.
Yeah. Okay, it's ui plus 1. Okay. So this is essentially ui plus 1
Yeah.
and then you have ui minus 1 at n,
Yeah.
so
Okay.
divided by delta x square. So for this again we have to just take that expansion. Okay, it just takes a little time to write it, so let me just complete it. Plus delta x times ux at n is delta x square by 2 ux6 I just write del cube u by del x cube. Similarly, you also have ui minus 1 n, which is essentially Taylor expansion around minus delta x. So this will be minus delta x times del u del x.
Yeah, we can just, yeah.
Del x square. Okay, sorry. So again, you will be having alternating plus and minus.
Minus, plus, and yeah.
3 factorial. Del cube u del x cube. And then you have a plus delta x power 4 by 4 factorial and del power 4 u del x power 4. Now we also have ui n plus 1. Essentially, you already have the expression for that.
Complete.
So now, as per the above equation, we were essentially drawing ui plus 1 n plus ui minus 1 n minus ui n plus 1 plus ui n minus 1. So if we were to do this, essentially all these, there are 2 plus and 2 minus, so this term goes off, and you are adding the 1 and 2 equations, so even this term goes off. So you will be left with delta x square times del square u del x square, and then you have delta x cube, the term goes off, even this term goes off, so basically odd term goes off, and then you will be left with delta x power 4 by 4 factorial into 2, so essentially that is 12 del power 4 u by del x power 4, and in the time domain we are just adding these equations, so the first term goes off, so these terms go off, so you will again be left with delta t square del square u del t square. So now what we are essentially doing is dividing this with delta x square, so that gives you delta x square delta t square by delta x square. So essentially, if you want to approximate this del square u del x square, so your this is order of delta x square, and this is in the order of delta t by delta x square. So now we have 3 terms. One is delta t square for our time discretization, and if when the space discretization we have delta x square, and also we have delta t by delta x whole square. So maybe if I write the equation now, if we write the equation using finite difference, then the equation we are trying to solve will boil down to the first equation del u del t plus delta t square times del square u del t square equals b times uxx is essentially del square u by del x square plus delta x square by 12 del power 4 u by del x power 4 plus delta t by delta x square del square u by del t square. Yeah, now maybe we should discuss about the consistency. So Nagaraj, Mr. Nagaraj, someone was speaking about consistency, Nagaraj, I guess. So you are saying something that delta x tends to 0 and
Yes.
maybe you can say you're trying to say something, yeah.
When delta x goes to there is convergence, right? What is consistency here? What is the difference between consistency and convergence?
Convergence is a different topic. So consistency is between your numerical scheme and between your analytical or your approximation scheme should actually be equal to your original differential equation. That is when you call
So-
your system as consistent.
It's consistent. Okay. So when you're what does convergence mean then?
Convergence is like as you refine your mesh further and further, the solution should be kind of approaching some particular value. It's like a summation terms eventually reaching some final value,
Okay,
right?
so the solution is now diverging, but when you mean consistent, I think you mean that when you reduce the spacing, it should essentially
Be equal to the
replicate or
original
repeat.
equation. Yes, that is what I meant by consistency. And like it's similar to like accuracy. If your solution is converging, that doesn't mean your solution is accurate. Convergence is a different issue. Convergence is basically depends on your numerical scheme as well. So just because your solution is converging doesn't mean your solution is accurate enough. So maybe for this particular differencing scheme that I have shown here, so if you see if delta x is tending to 0 and like if you try to make both of them equal to 0, so what do you think will happen?
Well, it should blow up actually because you have a limit problem, right?
I mean,
Delta
why
x-
would it blow up? I mean, both of them are tending to 0, so this will essentially be 1, right?
Yeah, that's right. Yeah.
So the equation you will be ending up is del u del t equals b times uxx plus some b times utt. So now you are getting a new equation. Like you are trying to solve only up to this part. Now you are having some. So essentially you are trying to solve a heat equation, but then you got a wave equation now. Like you are having double derivative both in time and space. So that will eventually give you a wave equation. So you are trying to solve one system, but you ended up with another system. If both are tending to 0, this is an inconsistent scheme. Now, with regard to accuracy, it is delta t square, delta x square, so it's a second order accurate scheme, but then it's not consistent. So you have to be careful when choosing your schemes. That's the whole point I want to make here.
In fact, sometimes we are neglecting the higher order terms, right?
Yes.
So truncation errors. So in fact, the solution it doesn't come to 0. In fact, it is
Yes.
approximate to 0.
Yeah.
So that is not when we increase the higher order, so we may have accuracy of that equation. I think.
Yeah, that's exactly that what you are calling is basically as you try to decrease your like in simple words, like if you try to refine your mesh, you should be getting accurate results in the sense that is possible only if your system is consistent in the first place. The difference scheme you have chosen should represent your original equation. Only then, if you refine, then it will match with the analytical solution.
Yes.
So accuracy, consistency, and convergence are three different terms. And then comes the stability. I think like maybe we'll take that up in the next one. As and when it depends on how your scheme gets as through iterations. Like if it is dependent on time dependent problems, then you need to be choosing schemes which are stable. In the sense, it should not diverge as you propagate in time, as you march across the time. So we will see that in the next week maybe. This week we will try to focus only on the steady state problems. So no time dependent ones. So only accuracy and consistency is where we deal with. So I hope this is clear.
Well, it's clear, but however, I have like one nice thing.
Yeah.
So if you take finite difference scheme, basically, so you have this artificial numerical diffusion term. If you might have heard this term,
Yes.
right? For the finite difference scheme. So we will add more. When you discretize it, automatically you are not solving the original equations. You are solving something else. So you add some diffusion so that your discretization is stable. That's why you
This is
add
one
numerical
such scheme.
diffusion.
Yeah, this is one such scheme. This is this term in between
No,
is added to.
I don't understand. Exactly. So now I don't understand. Obviously, when you're solving, you're not essentially solving something, right?
Yes.
No, I don't know why we are having issues with, like, we're not solving the correct equation. Like, you're having additional UTT. Maybe it is adding some stability. We don't know. Because you're not discussing the terms. So I'm not saying that. The
Sorry.
previous.
So the
No,
the
wait.
I didn't
You
get your
understand
point. No, no, I didn't get your point. Can you just repeat?
what I'm trying to say is,
Huh?
so in FEF finite difference method, if you
Okay.
I don't remember exactly what it is. When you're solving an equation, you discretize it. So you add something called numerical diffusion,
Yeah.
right?
Yes.
So that is UXX term or something. I don't remember exactly.
Yeah.
Just to
That will be
push
something like this.
Exactly. So even here, I see that additional term popping up, which is UTT or anything. So
Okay.
now what
Okay.
we
I got your question. So what you're
what
trying to
comes
say is.
is we are not solving that problem. This is not in you are saying inconsistent scheme.
Yes.
Just
I
because we
got
are
your question.
perhaps you understand? Yeah.
Yeah, so basically what you're trying to say, okay, I'll come to that. So you see here these two terms. So there is a UTT, before UTT there is a delta t square term. So UTT is there inherently, but the scheme you are saying, when you use when you introduce an artificial diffusion, the term we expect is something like this. So the coefficient will be dependent on your meshes. As and when, like, as you refine more and more, eventually your the significance of the term in your overall equation should drop out. But in this particular scheme is where if you try to increase your delta x, if you try to decrease your delta x, this term kind of gets more and more significant. That is something which we do not want. So this is not like an artificial diffusion term. So even when you add artificial diffusion terms, it can still be consistent because you will be having coefficients that will vanish as then you more and more you refine your mesh.
Yeah. Actually, I'm not disagreeing or agreeing with you, so I have no issues actually. So
Okay.
just that maybe there we kind of derive the equations. So from
Yes.
there we understand why we are adding each term. So here we are directly taking an equation and
It's
I don't know
actually
if we.
derived in the reverse way. So this is a scheme the
So I don't
instructor will
like
discuss.
me
Yeah.
to actually comment on it
Yeah,
further.
yeah.
So
Okay, fine.
let's
Okay,
move.
fine. We'll just move on. Yeah, you have some question?
In
Nagaraj.
fact,
Yeah.
yeah, there are some techniques. So finite differencing method. One is not techniques, methods, implicit method and explicit method, right?
Yeah.
So I hope we do not use the two methods in finite volume
No,
method,
no, we will
right?
be using. We will be using. We'll
We
come to
use
that. Like that is when you have your time marching, right? It's like
yes.
now initially we were dealing just with steady state, so we just it's not introduced, but it will come in the next upcoming lectures.
Okay.
Okay, then we'll move on to the next question. So this is a 1D conduction problem and on a uniform mesh. So we'll start with getting simple. So you have no source terms, but your diffusion term is spatially varying. So you have this particular functional form. So we start with the governing equation, and the question asks you to find the value of phi at this particular point, provided you know the values at the other two ends. It's like you know the value of this as 100, you know value of east as 400, delta x is essentially equal to 1. The question asks you to find the value of phi p, provided the governing equation is this. It should be fairly straightforward. So you essentially have gamma equal to 1 plus, and your domain is essentially having 3 units. This is my current cell, this is my west and this is my east cells. So this faces I am denoting by lowercase letters W and E. So this is the west face and this is the east face. So the governing equation is essentially steady state heat conduction in one dimension. So ddx of gamma, say our problem is phi, gamma d phi dx equal to 0. So the first step is essentially you have to get your you have to discretize your equations over your domain. So in finite volume, just integrate. I'm integrating over the pth cell. So I'm integrating over this cell. So my limits will be from the west face to the east face. So essentially the expression is gamma d phi dx, gamma east on the east face minus on the west face equal to 0. Now again, the next step is essentially to have expressions for d phi dx on the east and west faces. So we use a linear approximation where d phi dx on the east face is essentially phi east, the value of phi at the centroid phi east minus phi p by delta x. So if we use these expressions, we get gamma e times phi e minus phi p by delta x, and then you have on the west face. On the west face, if you want to calculate the d phi dx, that will essentially involve your to the right minus to the left. So phi p is towards right minus left is phi w by delta x equal to 0. So if you just rearrange these equations, the expression for phi p is essentially gamma e times phi east plus gamma west face times phi west by gamma east plus gamma west. So if my x coordinate starts at this, and I already know the equation for gamma, so what will be my gamma e? Gamma is essentially, gamma e is the value of the diffusion coefficient on the face. So that essentially gives you 1 plus x on the face, on the east face is essentially equal to 2 plus 3 times x square. So 12 plus 5, this is 17. And similarly on the west face, we have 1 plus. So on the west face, you are at a unit distance. So this is unit distance. The east face, we have 2 units. The total is given as 3. So delta x is essentially 1. So 2 times 1 plus 3 times 1 square. So this will give you a value of 3 plus 3, 6. And phi east and phi west are already given in the question. So phi east is essentially 400 and phi west is 100. So just calculate phi p over here. So it's 17 times 400, 6 times 100 by 17 plus 6. So this gives you giving you a value of around 321.74. So this is phi p. So this is how you approach it in finite volume. So the next question is essentially to calculate the diffusion fluxes. Okay, confirm that the conservation is exactly satisfied or not. So by conservation, what we mean is we calculate the flux on the west face and flux on the east face. Since there are no source terms and it is a study problem, the flux should be equal on both east and west faces. So like that is essentially the governing equation here. What this particular portion tells you is gamma e d phi dx is essentially the flux on the east face, and gamma w d phi dx is essentially the flux on the west face, and we essentially got the equation by solving that. So this will be naturally satisfied. Or if you want, you can just check by to be able to check, you will again solve the same equation, so you eventually get the same answer. Now we'll try the same problem using finite difference to see if it will really conserved or not. So now we take the non-conservative form of the equation and then we use a finite difference scheme as we use a central difference. So we have d dx of gamma d phi dx equal to 0 if we just expand it, we get gamma d square phi dx square plus d gamma dx d phi dx equal to 0, where d square phi, where this gamma is essentially you take the value of the node at which this equation is discretized. We are discretizing at point P, so I'm just writing gamma P and d square phi dx square. If we use a central difference key, phi E minus 2 phi P plus phi W by delta x square plus gamma is, we already know the gamma expression for gamma, 1 plus 2x plus 3x square. So t gamma tx is essentially 2 plus 6 times x, where x should be again taken at the node where this is discretized, so 6 times xp into d phi dx. We use central difference, so phi east minus phi west by 2 times delta x equal to 0. So our objective is to find the value of phi p. So phi p equals delta x square by 2 into gamma p by delta x square into phi east plus phi west plus 2 plus 6xp by 2 delta x into phi east minus phi west. In this equation, your delta x is essentially 1. Gamma p equals 1 plus, you just substitute the value of xp, where xp is essentially the x value at point P, that is 1 plus, this is half, so 1.5.
Vishal,
Yeah.
just wondering, why did you even, why did you expand the given conduction equation or diffusion equation? Can you just directly apply finite differences for that equation?
Then you would eventually get the same solution as your finite volume. So I was just trying to see, one is a conservative form, the other one is a non-conservative method. So we just want to see if we do non-conservative method, what happens.
Exactly, but now we will eventually prove that finite difference is bad because it is not conserving, right? Because you consider a non-conservative form, you consider a non-conservative differential form, and you apply finite, doesn't matter what equation you're dealing with, of course finite difference will fail. You see that?
So you are saying essentially, yeah, that is fine. So you are already accepting the fact that this is non-conservative, it is non-conservative form, so you're coming at it. Yeah.
Depends on the form. See, if you take the non-conservative form and if you apply finite volume method for this, or even you apply any other numerical technique, you're just solving, you're just approximating the functions. So it depends on how well you're approximating it. But anyways, yeah, I'm just continuing, yeah.
So I just got your point. So you already accepted the fact that it is non-conservative form. So the example is for those who didn't accept that. So I just want to show them that, see, if you consider this particular form, there is some problem, and that is what we are calling as non-conservative. So what essentially is not conserving here is something that I want to prove, or something that I want to emphasize on.
Okay, so but I'm just saying that since we consider, I think we should make it clear that it's not because of the finite difference method.
No, it's not. It's not because of the method. It's essentially because of the way you are solving.
Or the governing equation. So
Yes.
that we don't get into wrong conclusion that finite differences is bad, because so I am no advocate of finite differences. I don't use it, but anyways, yeah.
Yeah, it's not with the method. Fine. Thanks for pointing out. So if you just substitute these values, we get a gamma p of and we just substitute it, so we get 0.5 times into 500 plus fees minus P west is 300. Okay. Did I miss something? So I'm getting a value of 3512.5. I hope my calculations are correct. So, but it shouldn't be this far away. So even then you can see the difference here, but ideally this should match with this. In this particular case, maybe it is quite too high. It shouldn't be the case. Okay, we'll just go with this. So if you get a value of Vp by solving these equations, the next step you should be checking is essentially the fluxes on both the faces. So that essentially is gamma e d phi dx on the east face. And on the west face. We already have the value of gamma e. Similarly, gamma west. So if you try to match these two values, just show what there is. So this is some. Okay, even without solving, you can directly see over here that if this equation, say call 1 and 2, are essentially not equal. So this is essentially what we mean by conserving or not conserving. So the fluxes coming in and coming out should be matching if the method you are using is conserved. Otherwise, they just wouldn't match. Even though you might get the same value for Vp.
So I have some questions regarding fluxes actually, not regarding the method. So when you say flux, maybe I want to clear my understanding. Something is landing. So flux is generally a quantity moving across an area, right?
Yes.
So you just take a quantity and multiply it with velocity, then it get rate of passing. Right? If you multiply with the velocity.
Okay, it's like mass or some flux velocity multiplied by some quantity will give you that. Yeah.
So I'm just wondering why you are saying this diffusion coefficient or gamma times d dou phi by dou x as a flux.
This is essentially the heat flux. So if Phi is your temperature and gamma is your thermal conductivity, so that is essentially will be your heat flux, right?
All right. So and the divergence of that is actually the rate of like the change, right?
The net change. Right. Yes.
Yeah, that's great. Yeah. So we're coming from heat equation.
Yes.
Awesome. Okay. So we're looking at flux of temperature. Okay.
Yes. Yeah, you have some question, Nagaraj. Yeah.
Yes. So whatever the variables, or like gamma or velocity, whatever the quantities, so which are always the centroid of the cell, right? Only fluxes are the faces of the cell, right? Located.
Yes.
Only fluxes which are located on the faces of the cell.
Yes.
And the quantities which are always located in the center of the cell. Is it right?
Yeah, we are calculating only at the centroids. Yes.
Centroids. Quantities.
Yes.
Okay.
So okay, that will come in later section. So here I already gave you the function of gamma. So suppose you have dissimilar materials, then how do you evaluate the value of gamma at the junctions and all of that? We'll discuss in maybe next coming lectures. I think it will be discussed by the instructor in the videos itself.
So if the and one I have one more doubt.
Yeah.
The conservative non-conservative forms, if these forms have the same results, then why do we use?
No, they don't have the same results. I mean, same results in the sense your node values might be same, but the fluxes, you see, whatever is entering at individual elements, like if you consider only this particular highlighted portion, in that particular sense, whatever is entering may not be equal to whatever is leaving. So if that is not happening, then it doesn't represent the physical situation, right?
Okay.
So we prefer conservative because it is physical in nature. Okay, this is another problem where you have conduction plus radiation. Essentially, it's the same problem. So the only difference is in addition to the diffusion term, you have a volumetric source term. So you have a diffusion term and then a source term, but this source term is essentially some constant times phi power 4, or say phi naught power 4 minus phi power 4, or just to be consistent we will use temperature, T for temperature. So gamma dt dx plus T naught power 4 minus T power 4. So if you have equation of this particular form, when we try to discretize it, eventually our aim is to essentially get a set of linear algebraic equations, so then we can use some linear solver to get the answers. But the equation presented in this particular form is non-linear. Non-linear because your source term is again a function of your variable of your interest. So you want to determine t, but in order to determine t, you need to solve this equation. But to solve the equation, I need to know the source term, which is again dependent on temperature. So this is non-linear problem. So how do we linearize it? There could be like several different ways to linearize it. We can, if you are already aware of it, yeah.
We haven't been. I think we haven't been taught about linearizing this term. I don't know. If I missed something, maybe I'm wrong.
Okay.
Right.
So the idea is essentially use Taylor series expansion.
Okay.
So if it is not discussed, maybe we'll come. It's the you have S of t. So what you do is expand it around some reference temperature, some known temperature. So it's just this.
Okay.
So
okay,
we kind of neglect the higher order terms. We just consider only this particular form, so then it will be linear. That's the whole idea. So ds dt is again evaluated at the known temperature. T star is some reference temperature, where this will can keep on changing as you iterate in your solver. So maybe we'll take up an example next week. I think it will be discussed in the next week lectures. We'll take up an example on that.
Oh yeah, great.
Okay.
Combine.
This is a standard problem. So you have two parallel plates, both are stationary, and if you assume a one-dimensional flow, so this is the governing equation. You have the viscous term and your pressure gradient term. If your pressure gradient is a constant, and these are your boundary conditions, so it should be fairly straightforward to solve the analytical form, and then we'll use FEM to solve this. So your governing equation is essentially your Navier-Stokes equation for a 1D where all the fully developed flow and all those assumptions are taken. Essentially you have two parallel plates, both are stationary, and you have some velocity field, so you might be already knowing the profile, so it will be following some parabolic profile. So this is my y, this is y equal to 0, and say this is y equal to 1. So the boundary conditions are u of y equal to 0 is 0, like both the plates are stationary. So if you were to solve this equation, you will be getting u as some constant times y into 1 minus y, where this constant will again be a function of your pressure gradient and your viscosity terms. So it will be something, if I remember correctly, it will be something like 1 by 2 mu dp dx. It will be something of this particular form.
Just small mistake. Just you
Yeah.
know that, but u at y equal to 1 equal to
Sorry,
0.
sorry. Yeah. Thank you. So u at y equal to 1 is 0. So both are stationary. Yeah. So this is your velocity profile. So the problem essentially is to now solve this using finite volume method. So that we have that is being discussed in the class. So how do we start? Is again we need to have the first step is to essentially create your geometry. You're having something?
Yeah, geometry, of course. I'm just saying, just take the integral and we can just.
Yeah, you can just directly solve. Okay. So just to be consistent with the formulation, you start with this. So this is your
Geometry,
y
okay.
equal to 0 and say this is your y equal to 1. So the next step is to essentially discretize it. So you have some domains. Okay. So these are essentially your centroids, cell centroids, where your dependent variable like u values will be known. So say 0, 1, 2, 3, say 4. So you know the value at this is 0 and you know the value of u is 0 here. So now you take an integral over a definite cell. So if you just take say call this as I minus 1, I and I plus 1. So now if you were to integrate for ith cell, so this essentially comes from I minus 1 to I plus 1 d dy. I'll just write minus dp dx into dy equal to 0. So I think by now you should be familiar with this. So du dy at I plus 1 minus, actually I shouldn't be writing I plus 1 and I minus 1. So these are essentially your faces. So let's say this is my west face and this is my east face. So you'll be integrating from west face to east face. So this will be your east face and du dy again calculated on the west face minus dp dx into, so integral dy west face to east face. This is the first time. If you use the linear approximation, you will be getting on the east face. So you are having something like this. So this is your east face, this is your ith centroid, this is your I plus 1 centroid. So du dy at the east face is essentially ui plus 1 minus ui by delta y minus du dy on the west face. Similarly you will be having, now on the west face here you will be having I minus 1 cell and this will be your ith cell. So this is your ith cell, the towards left is your I minus 1. So same equation ui minus 1 by delta y minus dp dx into, as you integrate from west face to the east face, that will essentially your width of your one single cell. So that is equals delta y equals 0. So if I just group terms together and take my ui towards one to other side, so I'll be left with 2 mu by delta y ui equals mu by delta y ui plus 1 plus mu by delta y ui minus 1 minus dp dx delta y. Maybe I can simply write as ui equal to ui plus 1 plus ui minus 1 plus minus 1 by mu dp dx into delta y square. So I think this is for your a single cell, like for the interior cells. Now on the boundaries, where you have boundaries, it's slightly different because like if you just put I equal to 0, then you wouldn't be having I minus 1 term, and similarly on the other boundary. So for the boundaries we need to treat differently. So like detailed discussion will be done in the lecture videos. So I'll just take a simple example where you are on the left boundary. So this is
Yeah,
your,
I remember, so I think you actually extrapolate the point on the left, right? That's what you do. That's what I remember Professor doing.
yeah, we can just do in several ways. So I'll be discussing a simple way.
Yeah, I agree. Also, it depends on what kind of boundary
Yes.
condition we are trying to enforce.
Exactly.
Right?
It depends on the boundary condition. Here we have
So what-
Dirichlet condition.
It's like you know the value. It's not the
I know the
derivative, right?
value, exactly. You know the value. So the thing we are doing is something like, say this is your leftmost cell. So for the leftmost cell, so like for this particular 0th cell, if I were to discretize, so the equations remain the same. So this is my east face and this is my west face. So for the east face, it will be u1 minus u0 by delta y minus, for the west face, you start with u0 minus, but you don't have any cell, any point towards your left side. So what I am essentially doing now is I am just taking the boundary value by, but take only the half. So essentially it will be delta y by 2. So this approach I will be using. So if you just take this.
There's one interesting question I have here actually.
Yeah, go ahead.
Okay. So what do you think the accuracy of the solver would be now?
It will be of delta y, right? I've just used a linear interpolation, so it will be a order of delta y, right?
That you want to approximate a function, however you don't have derivative over there.
Yes.
So how do you think it affects? Of course, I think in the cells which don't have the boundaries, I think we can have the guarantee of the accuracy. Like whatever accurate, however accurate I was. You understand what I mean?
No, I didn't get you.
What I'm trying to say is, in the cells which are not on the boundaries.
For the
so
cells
you
which are not
take
on the boundaries, okay.
Okay. So I think whatever the formulations we have followed in FVM have some accuracy, right?
Yes. Okay, I got it. Okay, so you are essentially
Like-
saying it might be different in the interior cells and the boundary cells, right?
Second order accuracy, third order accuracy.
Okay.
So since at the boundary we are not, I don't know. So I want
Yeah,
to
I
ask,
got it. Okay.
understand? Maybe it will be different from what. Maybe it may not be the same as how it is in the center cells.
Yes. That is definitely the case. Your boundary accuracy will be different from your interior cells.
Yeah, it will be interesting to look. Okay, yeah.
Yeah, they are different, but it is observed that that actually doesn't significantly influence your final results.
No, I agree. It doesn't
Yeah.
significant. I'm just asking like in
Yeah.
quantitative sense.
Yes,
Quantitative,
they are
not
different.
qualitative. Yeah. I mean, you get the answer, but
Yeah.
I'm just seeing how it mathematically quantitative.
Okay. So if you consider these equations over here, now if you group the terms, your unknown is essentially your u0, not unknown, but you want to write equations in that same form. So for u0, you'll be having, say, 1 by 2 term here and 1 term over here. So 3 times u0 equals u1, and then you have a boundary term minus, or maybe I'll just write in the same format, minus 1 by mu dp dx into delta y square. So this will be on the left boundary. Similarly on the right boundary you'll have the same equation, but the boundary value will be towards your right. So maybe I can just write it down. So this will be your final cell. So this is your last but one. So I am writing equation, discrete equation for the nth cell. So this boundary value is something I already know. So the equations will be like mu times on the right boundary on the east face. This will be my east face and this will be my west face. So on the east face you will be writing ub minus un by, I'm just discreting over half cell, so delta y by 2, minus similarly on the west face you will be having un minus n minus 1 cell by delta y equals 0. But to group the terms again here, so for the un I'll be having 3 times un equals, you have un minus 1 plus ub, and then it's a similar term, so minus b dp dx delta y square. So for all these finite volume formulations, the notation like professor will be following is something like you have ap up equals a east u east plus a west u west plus some b. So this is the form we will be using. So this is your coefficient for the east and for the west, or in the indicial notation if you want to write, so ai ui, or maybe I'll just write api ui. Essentially a east is something like I plus 1 ui plus 1, a west is something like I minus 1 or Okay, let us be consistent. So for the ith cell is what I am writing like this. So u I minus 1 plus bi. So this AP, AE and AW are essentially the coefficients that you need to get from these discrete equations. So in our particular scenario, so like I is essentially your grid point, I mean cell centroid number, or maybe I'll just call cell centroids. So your coefficients only for the first cell centroid I equal to 0, you have AP of 0 essentially as 3, A west, or maybe let's put it in a table form so it will be simple. So I'll just write AP, A west, A east. For I equal to 0, I have my AP, this is my AP term, and okay, the other terms are just 1. So and B, so AP is essentially 3. For the first cell, there is no west neighbor, so AW is 0, and for the east neighbor, the coefficient is 1. B is essentially your term over here, so I'm just calling it's just minus 1 by mu dp dx delta y square. For all other intermediate cells, for all the interior cells, we have this equation where your AP is your first term, so that is 2, A west and east are 1, and this essentially will be the same. For the last cell again, AP will be, it is from this equation. So AP is essentially the first coefficient of that particular cell, so that is essentially 3. And for the last, on the right boundary, you don't have any cell towards east, so for the west coefficient will be 1 and east coefficient will be 0, and the source term is essentially the same. I mean the B term is essentially the same. So this is what you get. So I thought maybe we'll, instead of solving it by hand, we will solve using Gauss-Seidel elimination, Gauss-Seidel method. So last week some of you already told that you are already aware of Gauss-Seidel, so I thought I'll just give a brief for those who are not aware.
Yeah, I think this was discussed in the class. I think it is like.
So you are already comfortable with it, yeah.
But it is not detailed in. We'll do it in next week. I mean, I'm not saying we should not now. I think he discussed what is Jacobi and what is Gauss-Seidel. So it's like you have the iterative technique is one thing, and you have inverse, which is not what you take. I think
so basically direct methods and iterative methods.
Is that what Gauss-Seidel is?
Yeah, Gauss-Seidel is you guess some value and you iterate till you converge.
That's what Gauss-Seidel is.
Yeah. So it's the simplest of all the methods. So I thought maybe we'll use that one. So last week they told they would like to see this. So.
Yeah, sure. Okay, I'm sorry.
So the idea in Gauss-Seidel is something like this. So you have some equation. So you have some equation of this particular form. So the first step is essentially guess all the values of phi.
I have just one question actually.
Yeah.
So in the previous, like the equation above, just above Gauss-Seidel, AIP UI equal to. Yeah.
This
just
one.
right there. Yeah.
Okay.
I think you have to move this AIE and AIW to the left and solve their system, right? If I'm following it correctly.
That is a direct method.
Okay.
Yeah.
So okay. I think actually we don't know the value of AIE and AIW and AIP.
No. We know the values of the coefficients. So basically, we know the values of AIP, AIE, and AIW.
Oh.
Unknowns are your UI plus 1, UI minus 1.
I'm sorry. So you want to know UI plus 1,
Yes.
UI minus 1.
Yes.
There are 3 unknowns and like several equations. Oh, great.
Yes. So that is where your direct method comes. You just take to the left and then you form one matrix and then solve. That is your direct method. And iterative method is where your essential equations are of this particular form. So you start with a guesswork phi, and then what you do, or maybe we'll just take the same equation, like just to avoid confusion. So if you just take the same equation, you start with an initial guess over the entire domain. So for all I equal to 0 to n, you start with a guess value, and then you update the values as in for each UI, you just take the same equation. Yeah. So previously there used to be some value, now you update that value using this equation, and then you go on for, you repeat this for all the values of I. So like say for I equal to 0 to n, you update all the values, and then you keep on doing this till your error is within some tolerance. So error is essentially your whatever is the value of u before you start your iteration. So you have some you started with some initial guess u0, so you have a u value now. So error is essentially say L2 norm, so u0 minus whatever u you have now. If you just take I'm just writing taking an L2 norm, so essentially you take a summation of all the terms, and then this entire thing will be repeating till this error is within your tolerance. So that is essentially your Gauss-Seidel method. So I thought maybe we'll see through some code. It's stupid. So I hope this is visible, right? Yeah. So this is the problem we are trying to solve. So for the two parallel plates between both top and bottom velocities as 0. So I'm taking a value of dp dx by mu as minus 10. So these are just a problem parameter. So I'm just taking a grid point with say 50, or maybe we can just try solving with a smaller one first. Say 5 grid points. So essentially you have 5 nodes or 5 centroids or 5 unknown velocity components that you want to find, like u0 to u4. These are my initial conditions. So to solve the problem, what you essentially need is you have to initialize your initial velocity over all your grid points. So that is this particular statement. So what this statement does is it creates an array of n grid points, and each of them I'm just giving a value of 0.5. If you want, you can just give 0. It's like I'm just giving all the velocities as 0. And since there are n points, your grid size will be essentially 1 by n. 1 is my total length, so 0 to 1, so you have 1 over n. And then now I have all the coefficients. So from our previous equations, the west coefficients are all 1, east coefficients are also 1, and the coefficients of the center node or whatever is the current node is 2, and this is my b term. These will be changed only on the boundaries, where your boundaries, this is the leftmost boundary. For the left boundary, you have a west is 0 because you don't have a cell towards the west of the left boundary, and your ap value is 3. Again on the right boundary, it will be just towards like your east coefficient will be 0 and the current node value will be 3. At both the boundaries, your b value will be essentially incremented by the corresponding value of the velocity value at the boundary. Since here we don't have any velocity components, the term it won't add anything, it will be just be 0.
Yeah, so I have a small question here.
Yeah.
We have this primary centroids of the cell, right, which is denoted by capital letters.
Centroids.
So if we
Yes.
if you have 3 cells, we have
0,
3
1,
centroids.
Okay.
So we have 0, 1, 2, let's say they are centroids. Then also have these boundaries, right, which are so the total number of points. So how are you differentiating between centroids and
So boundary is essentially on your face.
so there are 3 cells. This will total 4 points if I'm not wrong. Am I right?
If you have 3 cells, you have 3 center points, 3 centroids. So there is only 3 unknowns that I will be solving. I won't be solving for the boundaries. Like it's for a Dirichlet problem. I already know the boundary values, so I don't have to solve for them.
Yeah. So no, I'm just talking about the mesh because I don't see any small e values. Small e values where you compute the flux at the face, because you need those values as well, right? I mean, where are you saving the flux?
I am not calculating flux as of now. My objective is to find the velocities, not the velocity flux, right? I mean, not dou u by dou y.
Okay, so you discretized it and you finally, so you don't need the small e values at all. Is that what it is?
Yeah.
Okay, so this
Our objective is to find the velocity, right?
Okay, I think after further like deformation, we finally got this scheme
Okay.
which only deals with the centroid values,
Yes. So
right?
this is for
And
the
you have
discrete
like,
equation. How do you approach Gauss-Seidel to solve your discrete equations?
okay, just a moment. So you have total 5 points, if I'm not wrong, right?
Yeah, if
Five
you have
points, three
five,
centroid.
5 points,
Okay.
5 centroids. If you have 5 points, essentially mean 5 points are essentially each centroid is your unknown.
Yes. So then you have total 7 points to solve the system because you have two boundaries.
I'm
If
not
you have to
actually
solve.
considering boundaries because I already know the boundary values, so I don't have to consider them. I mean, I already know the value there, right?
Kind of adding them in the scheme and
It
stuff.
just goes into the equation. That is essentially your this b term. I already added them into these equations, so those two terms
Awesome,
are gone.
awesome.
Okay.
Yeah, I got it.
Okay. So now for the Gauss-Seidel, it's again you have to define your tolerance. So the only difference between direct and iterative methods is in a direct method the problem is solved to the level of mission precision, but in a sense, say if you're okay, I'm not aware if you're I'm not okay, I do not know if you're aware of this mission precision term. So basically, you in all your physical problems, you have to know the say if your velocity is unknown, you can measure velocity only up to a certain precision. So if it is fine if you solve only to that precision, but if you use a direct solver, it will try to solve to the level where, say if you use a double variable, the direct method will give you an expression that is precise up to the level at which the mission it is mission precision. Say if you use MATLAB or something, for that double value you will have 10 power minus 64, or say 10 power minus 63 or 10 power minus 60. So it will give you an answer of that precise, which is not always necessary, and it is of no use to us because we will not be able to measure to that level. So in Gauss-Seidel you will specify the tolerance you require. So I'm just giving a value of 10 power minus 6. So this u nu, okay, we'll come to that later. So the iteration essentially has two loops. The first loop is to track your error and the second loop is essentially to go over all the points within your all your grid points. So initially you set an error equal to 0, and then what you do, you iterate from I equal to 0 to n is for all your interior cell centroids. So for the first cell centroid, you don't have a west cell, so the equation is a east into ui plus 1 is essentially your value of u at the next centroid, plus you have a bi term divided by ap of I. Similarly for the last cell, it will be towards the west, and like you won't be having an east term, and for all the interior cells you will be having a west term ui minus 1 and then a east term ui plus 1, and your bi is b term, and then you divide it by ap of I. So once you calculate the value of u, then you update your error term. Error term is essentially this ui is not updated till now, so this is the previous value or your guess value minus whatever you get currently. I'm just taking an L2 now. So after taking the error, you just update your velocity, and then this loop will again go to this while. It will start from the while loop. Again, it will try, if the error is again above the tolerance value you have specified, it will again kind of update the values. This keeps on going till your error is within the tolerance, and once it is out, you will have a value of. So it comes to this loop. So you get the value of u, and this set of code is just to write it into a text file. I've already computed the analytical solution, so you already know the analytical solution. So it's of okay. I've just written the equation here. So it will be something like y into 1 minus y into some constant. So just to compare how the analytical solution matches with FVM. So few set of other codes are to just plot this thing. Maybe I'll just. So this is how, I hope the numbers are visible. So this whatever is printed here is the error at each iteration step of the Gauss-Seidel method. So initial guess, when I gave a value of 0 over the entire field, the initial error is of the order of 0.4, and then eventually it kind of converts to around 10 power minus 7. That is where your iteration stopped. So if I just take make a plot of this, I have like I used GNU plot for that, so I already plotted that. Okay. like they are already quite well matching with each other just for 5 nodes. So okay, it just matched, but even like in general problems it might not just match, so you have to check by increasing your number of so this is where your convergence comes into picture. You try to refine your mesh and see your results are converging.
So I think, can you go back to your plot once?
It seems to have not been updated, right?
Yeah, actually, because can you go back to the plot, just PNG plot once?
Yeah, it has more number of points.
Yeah,
It is not just 5 points. Yeah, I've seen that.
So
I'll just run
you
it
might
once.
have several cases.
Yeah, I've just run
Yeah,
it.
yeah.
I've just run it again.
That could have happened.
Yeah, now it
plot
is clear.
Again, yeah, if you plot it now, you just had plotted again.
Yeah, I just plotted again. Now you can see the difference between the analytical one and the FEM solution.
Yeah.
So now there is some quite a difference. So usually they might not converge. So you have to just refine your mesh to see how well it converges. So maybe we'll try with n equal to 10. Okay, for n equal to 10 it kind of got converged. So what do you think if we put n equal to 100? It will converge?
It should ideally, no?
Okay. Okay.
Oh.
Okay. What do you
Okay.
think is happening?
But I mean, our scheme is consistent, so ideally, if you're changing the spacing, it has to work. So I don't know.
Okay, consistency is different from convergence. Consistency is because of the scheme is consistent. Consistency has nothing to do with convergence.
Is our scheme not convergent?
No.
Convergence in the sense, so we need to see that results come to steady state or not. So when the results are come to the steady state, so it could be the converge. So otherwise the results will not come to the that steady state. Results will be blown off. Divert. The results will be diverged.
This is study problem. What do you mean by study?
So I think what he meant by steady state is if you keep on changing your mesh size, the results should be identical. So for n equal to 5, if you have some value at n equal to 10, the value should be closer to that one. As you increase your n, the differences between two successive values of n should be kind of reducing. That is what you meant, right, by steady state?
Yes.
Okay.
So there are a few things here. One thing is you might have coded it wrong. Okay, we'll leave that. Few points are there. Okay. The second thing is the scheme we described is actually convergent scheme. So scheme as in whatever the final algebraic equation of system we derived. I think it is convergent. That's what I understood with the way we went through.
Okay, maybe we'll just go through the equations once. 1 second.
Yeah.
So where is the equation? Oh, so this is the equation. So we'll just take the general equation.
So yeah, so this is we did. Okay.
Okay. Now what do you see here? As delta y tends to 0. If delta y tends to 0, what is happening?
Okay.
This particular term will just go off, so your equation will be more or less doesn't see any pressure gradient term.
Okay.
So but how did we get this equation in the original problem? So originally we'll be having something like this. So I just multiplied with delta y to it's like we have some original equation like this. I just multiplied throughout with delta y to get the above equation. So like that's how I got it. But ideally it will be like these terms will be too high, and it's like this and this term will be negligible, but then the difference will match out to each other. It's not it's not like it's inconsistent. It is consistent. If you try to expand this Taylor series expansion, you will get the same expression as the original equation. It is nothing to do with the coding. The problem is somewhere else. So any other cases that you think might be the reason?
Coding is fine. I have no issues with the coding thing.
Yeah, it's not a coding problem as such. It's something else. It's with the numerical method. It's with the numerical method.
That's what I'm trying to.
Yeah.
understand.
Yeah, maybe we'll wait for some time, no issues.
I don't know, man. Maybe you can. Yeah.
Yeah, okay.
It's too hard to guess the wrong thing like sitting here. You understand?
Yeah, okay. No issues. It's like if you come across a new point, then it will be beneficial for others as well.
Yeah. Just thinking. So maybe the way we discretize. So I remember that this scheme is consistent. Like this is only we extrapolate it like linear. So the variation of phi through the cells is linear variation. That's what we assumed.
Okay.
And maybe that might be the problem. Maybe we should assume that it is not linear variation. Maybe it is parabolic variation. Maybe that will solve this problem. That's what the one more guess I have.
Okay, so
Because
we'll come to that point first. If you have a linear profile, as you refine your mesh further and further, your approximation will be much better, right? Ultimately, any curve can be linearized if your delta x is too small.
No, what I mean is, say in finite difference technique, so the one of the things which Professor haven't discussed, if I think I'm right, he didn't discuss about the accuracy of the discretized scheme, like how accurate the discretized scheme is.
Okay.
But in finite differences, in the first problem itself, we said it is order of delta t squared accurate, delta x squared accurate. We haven't discussed any of those stuff. So that's where I'm putting the blame. I don't know. Now you have to tell me.
Okay. That will be discussed maybe in the next lecture. He will be discussing in the next week about the accuracy of your finite volume schemes. Okay, but it has nothing. Okay, I'll just give you an example here. So the problem is something to do with your Gauss-Seidel method. So I've just kept a tolerance of around 10 power minus 6.
Okay.
So
that's nice.
Here what happens is if your delta, as your delta y is very small, your b term is essentially because the tolerance is low, it will assume b is 0, and then it just won't give you any updates. So maybe if I reduce it further.
Okay, so I have one small suggestion.
Yes.
For the Gauss-Seidel method, can you add one more variable saying tolerance and also the size? And can you add this tolerance thing? Let's not hard code it. Let's add it there so that it is, because we will always forget, right? Like what is the tolerance? It's actually coding paradigm I'm discussing here. So that will be easy for us, for me, like me, like to like if you hard code it, next time when you run it, you have to go there and change it. But if you actually pass the function, you can call different functions, and it will be easy for to keep track of the sort. I mean, I don't know. I should not say
exactly.
I don't know.
Yeah, but I would have done it before. You would have figured it out much easily, right? I just don't want to do that. I just want you to think.
No.
Yeah, that is fine.
Point. Whatever.
Yeah.
I'm not saying that good program. This is really good program. Whatever you're doing is really good, according to me. I'm not saying that, but just that usually we pass. Then it is easy to.
Yeah. I just made the changes, so you can pass the tolerance over here, or maybe I'll just make it even more general.
Yeah, that's great. Yeah. So usually we do some command line argument, minus tolerance, or something like that. We do that. Yeah.
Okay, I think the point I want to make here is when you try to define, like if you are using an iterative method, you need to be careful with your tolerance and your meshes. Both have to be kind of chosen appropriately. Only then your results are kind of makes physical sense, or before talking about your accuracy and convergence, you need to ensure that both are of taken care appropriately.
See, because I don't know, I was like we even if it takes some time, I would have blamed, like I would have printed everything and checked. That's how it is. You start blaming everything, right? You don't know the problem. You start looking from the bottom.
Exactly.
That's why you write tests.
You have to have test cases.
Yeah, you write test cases, you test development, all the stuff. Anyways, yeah. Thank you. It's really great exercise actually.
And
so can we have this files by the way, or are we supposed to code it by ourselves?
Yeah, I don't know if all of you are familiar with C++. You will be using your own language.
I am familiar. I'm talking for myself.
Okay.
Can I have it?
Yeah, I'll share this. I'll share it in the Google Drive.
Maybe I will.
Is it C++?
Yeah, it is in C++.
Okay, maybe I'll put the link. I don't know, because I don't see anything about the recorded lectures on the forum. I don't see the
it's actually there. It's actually there in the lecture videos. Like just beneath your lecture videos, there is an option for all this recording. No, not the feedback. Below the feedback.
Okay, so if it's there, so please don't. I want it like because I can do it by the next week. So because I'm trying to maybe
No,
I'll
these
try
will
to,
be uploaded just after the class.
yeah, that would be great because I will try to what we say that transpile. That's the right word.
Okay. So maybe you, okay, this is just an hypothesis. So if you see, the
Transpile
problem here
something, yes,
is,
yes.
yeah, if you are having for a Gauss-Seidel method, you need to specify your tolerance. But as I told before, if you are using any direct method, say if you just take A inverse, x equal to A inverse into B, it will just solve the equation to the mission precision. So if you are using a direct solver, then you will be having these problems in the first place.
So
If your
I
matrix
have
is
this.
non-singular.
That's good. Yeah, that's where I was going to actually. If you take a problem with there is no, if it is periodic, towards like every there's no boundary.
There is, okay, periodic boundaries, okay.
Periodic, so there's no boundary actually in periodic
Physical
boundaries,
sense,
right?
okay.
So then the term B would be 0. How would you solve that problem? But there's more Gauss-Seidel. Okay, let's go back to the finite volume method, of course.
Okay.
You
It's
understand what I'm
not
trying
about
to
the
say?
solver. I understood your point. It's not about the. Okay, you
Yeah.
can use a different solver. That's up to you. You can use direct solvers.
Okay, yeah, great. That's something else to discuss
Okay.
anyway. So this is something
Okay.
good to touch upon for
So
others.
the next problem essentially is again is the same. Is a parallel plate flow. Now the problem is you already know the velocity profile, but you need to find your temperature. So this is something we have been. So first let's go through the question. Okay, sorry for this. I have to switch between these things. So it's the same thing that we have discussed previously. So now we want to solve for the temperature equation. It's again the same parallel plates. You have two parallel plates, both are stationary. The problem is to get the temperature equation. So if you recollect, we have the temperature equation as rho c dt equals something like minus p del ui del xi plus plus some viscous dissipation term. So this is some equation we were having previously. So if you take a steady flow and incompressible flow, both these terms will be okay. I just can't say this term is 0 just because of steady flow. You also have it essentially has two terms. So you have a time dependent term and you also have a convective term. So I'm essentially neglecting these two terms, or maybe you can consider it as I'm using a fluid where your specificity is very low compared to your velocity, so that is where your Eckert number comes. So this particular term is essentially negligent. So now you'll be left with this particular equation. So for a 1D, you have k time, or say for parallel plate, this is my x and this is my y. Or let me put on the top. So this is my y equal to 0 and this is my y equal to 1. So my y is essentially going the other way. So I'm just saying this is an adiabatic one. So I just insulated it. And the top plate is at some temperature T, some temperature. So I'm giving it as a value of say 300 Kelvin. So the objective is to give an estimate of the temperature inside this. So if previously if we have neglected the phi term, so you essentially have, say you have a fully developed flow where I shouldn't say fully developed, but okay, let's consider its velocity, as per velocity is concerned, it is fully developed, so you don't have del u del x terms, and it is also thermally developed, say, and the conduction along the x direction is negligible compared along the y direction. So what I mean to say is if you expand this, I'm just saying like along x direction this is very small compared to the gradients along the y direction. If that is the case we are trying to solve, so we'll be dealing k times del square t del y square plus phi equal to 0. If we would have neglected the viscous dissipation term, what we will eventually get is something like it's a normal conduction equation. So now just because this viscous dissipation is your source term, that we discussed previously, because of this source term your the kinetic energy of the fluid will get converted into the thermal energy of the fluid, and that will increase your temperature. So essentially on the bottom is insulated, so the heat doesn't have any way to escape. So that should actually increase the temperature near the bottom. So this viscous dissipation term, like if you recollect, we have something like 2 times del u del x square plus del v del y. I'm just writing for a 2D case. Plus you also have del u del y del v del x square, and the remaining terms will be like del u del z. There is no third term, so you'll be left with only these things. So out of these, again, if we are just considering a one, so V is essentially 0. You don't have V in parallel plate flow, so this for a fully developed flow, this term also goes to 0. So del V term is also going to 0. So we're essentially left with phi equal to mu times del u del y whole square. So we just plug it back, we get k times plus mu times, okay, since u is only a function of y, I can just write du dy. Similarly, t is only a function of y, so I can just write d square t dy square. So we already know the velocity profile. U of y is some constant times y into 1 minus y. Just plug it in back. So du dy essentially a into 1 minus 2y. So you'll be having d square t by dy square plus some constant k into 1 minus 2y whole square equal to 0, and your boundary conditions are essentially at y equal to 0, I am saying temperature is a constant temperature, and at y equal to 1, I am saying it is adiabatic. So this comes down to saying dt dy at y equal to 1 equal to 0. So these are my boundary conditions. So naturally the first step is again is to have your grid from y equal to 0 to y equal to 1, and then you to have your cells. So say 0 1, so I have just 5 cells here, and here I know the value as dt, and here I have dt dy equal to 0. These are my boundary conditions. So unlike the previous case, here we'll be having a Neumann kind of boundary condition. So let's say this is I minus 1, this is I and I plus 1. This is the same as the previous problem. So if you just discretize it, you just integrate from say west face to east face. So you have t square t by dy square. I'm just calling the second term as this k into 1 minus 2y square. I'm just calling it as some s. So your original equation becomes d square t by dy square plus some s equal to 0. So west to east s dy equal to 0. And by the way, this equation is linear or non-linear? There was some confusion previously when there is a function of space.
This is linear equation, right? Because there's no variation in T.
No variation in temperature, so it's a linear equation. So it should be straightforward to kind of implement this. So this first expression will kind of give you dt dy along east minus dt dy at west face plus how do we approximate it is for the pth cell, if you are staying as p, or maybe I'm using this confusing, it might get confused, so I'll just use the indicial notation. So I'm just calling it as SI. SI is essentially S calculated at the value of P times delta Y equal to 0. So
I have a like about linearity and non-linearity. Even though it is linear, I was just wondering why this scheme should not work if say that you have a constant to d square t by, let's say is a times d square t by dt square, and say that a is t square. Can you just write additional equations, right?
Okay, so you're saying t square times d square t by dy square
dt square times dy
equal to plus some s equal to 0.
something equal to 0.
Okay.
So why don't you think why can't we use FVM here? We could just take integral.
No, I'm not saying you can't
Integral.
use FVM. You can use FVM here also. The problem I'll tell you is, say if you
True.
take the east face, so this will give you something like this, right? If you discretize it.
Okay.
So you will say you will put T east there. Something like that is what you're saying?
Yeah, you didn't say it won't work. I'm not saying that. I was just wondering why
Yeah, the
even
problem
in
is the temperature itself
we
is unknown,
always say
right?
we want to use linear equations. You just take this and we can solve this, right?
We can solve
Maybe
this.
how?
The linearity I meant there was when you try to discretize this, eventually you get some system of equations, right? Those system of equations are linear.
Okay. I mean, maybe that will become nonlinear probably.
Yes,
And
if
you
you
need to
have a
use
nonlinear,
nonlinear
yeah, if
equations of solving and
yes, you need to
okay.
use some Newton-Raphson and all of that. So if
Okay.
you have a
And
nonlinear
maybe
equation,
so like one more thing, if so whatever the discretization we talked in FEM, it is we never discussed about the order of the equation we are trying to solve. Like if the order is maybe it's nonlinear. Okay.
okay, you
We
have a
discussed
nonlinear
about
equation. It's like Navier-Stokes equation. You have Navier-Stokes equation.
you just take some equation
Okay.
and say that you're using FEM. So it is never about the equation we are dealing with. Like
Yeah.
like even if you're dealing with higher order equations, I think it has the accuracy or anything of what FEM is discussed is not affected by the equation we're trying to solve. I think they're independent. Maybe
Huh.
I don't know.
It
If
doesn't
you
depend on
understand
the
what I'm
equation,
trying
right?
to say.
Yeah, yeah. The method is
Right,
independent
right.
of the equation. Yes.
Yeah. Okay. Yeah. Good.
Yeah, the only problem you'll be having is if you start with a nonlinear equation, the set of after discretizing you will again be left with some nonlinear equations. Solving them is again difficult. So we try to linearize in the first place. So again, we coming back to this question. So dt dy by on the east face will essentially be ti plus 1 minus ti by delta y minus along on the west face you have plus si times delta y equal to 0. So this is something similar to what we have previously. So we have 2 times ti equals ti plus 1 plus ti minus 1 plus si times delta y square. So this is for the interior cells. I think left boundary is straightforward. It's same as our previous case. So you have the 0 cell and first cell, and you already know the value of t here. So I'm just calling it tt. So if you discretize for the 0th cell, for this particular cell, you have dt dy. This is my east face and this is my west face. On the east face it will be t1 minus t0 by delta y, minus on the west face it is t0 minus tt by delta y by 2, and there is a source term si times delta y equal to 0. So this should give me the equation is written for t0. So for t0 you have a coefficient of 3, and then you have a t1, and then you have 2 times tt, and then you have si times delta y square. So this is on the left boundary. On the right boundary is something different from the previous case. Previously we know the value on the right boundary, but in the current case we just know the flux on the boundary. We do not know the actual value. So this is my nth cell, this is my n-minus cell. I am writing equation for the nth cell. So I know the flux already here. This is my east face and this is my west face. So the equation itself is like dt dy on east minus dt dy on west plus Sn times delta y equal to 0. Since I already know the value of this, I will just substitute the value over here. In this particular case it is an adiabatic on the bottom side, so essentially this term goes to 0. On the west face you will be having tn minus 1 by delta y plus Sn times delta y equals 0. So if you just take the terms as tn is your unknown, so tn equals unknown in the sense we are writing equation for the nth cell, so I am just taking to that left. So tn equals tn minus 1 plus Sn times delta y square. So this is on the right boundary. So if you write the general equation, if you compare with the general equation, AP TP equals A East T East plus A West T West plus some B. So we have A East, A West, AP and B. For I equal to 0, that is this equation. For I equal to 0, we have a coefficient of AP as 3. East is essentially 1. West, we don't have any cells towards left of it. So we have 0. And your B term is essentially S1 times delta Y square. Oh, sorry, it should be S0 maybe. I written it as S. It is essentially S0. You are writing for 0th cell. So for all the intermediate cells, interior cells, I to n minus 1 is this equation. So your coefficients are AP coefficient is 2, A East and A West have 1, and this will be SI times delta Y square. And for I equal to n is the last equation. So AP is the first on the left hand side coefficient is 1, and for the right boundary we don't have anything on the east, so this is 0. A West is 1, and B term is Sn times delta Y square. So these are your set of equations. The boundary conditions are already incorporated into this. So if you solve this set of equations, you should be getting an answer. Okay. So maybe I've just written it's just the same code. You have to just make some few changes. The only changes will be like you have your initial condition is again given in terms of temperature. So this is your initial temperature that I am giving as 300 Kelvin, and then in the solver again you have all defined the coefficients. So AW is essentially 1 always, A is 1 and AP is 2. Only on the boundaries these things change. And coming to B, I defined initially B as zeros, because we have so B term is essentially varying with the value of y, so I've just written another function to take care of that. So it follows the particular form as some constant times 1 minus 2y whole square. So I've just taken the constant as 10. So we just substitute these values here. So this is how we update the values of B. So B from 0 to n. Now again, in addition to these, when you have other boundary conditions near the boundaries, you need to update your coefficients again. So on the boundaries, again on the left boundary you don't have a West condition, so AW is 0 and AP value is 3, and because you have a Dirichlet condition, your constant B term will also have an additional term, so that is 2 times TW. So this we have in the original equation. On the east boundary, it's a new Neumann condition, so you have A East essentially 0 since you do not have anything towards east of the last cell, and AP is 1. And for the B term we don't have any addition because it's like the flux is already given there, so your B term will essentially have this particular equation. So whatever you get from this equation will be your B term, so it doesn't have any additions to that. So the Gauss-Seidel implementation is same as the previous one, so you just iterate it till your convergence. So I kept a tolerance of 10 power minus 10. So I've solved it for like grid size of 2 points, 5 points, 10 and 20 points. And these are the results. Okay, it may be not that clear. It's like after a certain point it will just converge. Okay, it's not okay. You see that the temperature difference is not that high, it's like only 1 Kelvin higher, so you might not just notice. It's only when the flow is high speeds is when you see significant temperature difference. Still the implementation is straightforward, it's the same as the previous code. The only difference between the previous and this one is here we have the on the right boundary we have a different boundary condition. That's the only difference.
So what you're trying to say is you have this flow. Can you see me? Yeah, you see me. So there's this flow, like parabolic flow, and we have temperature over here, like height, like we are heating it. So we have constant temperature here, right? Mm-hmm. Right? And you have adiabatic, like there's no temperature, zero temperature maybe. Zero temperature?
Adiabatic.
Yeah. So water
Adiabatic
Yeah,
in the sense no
adiabatic.
heat flux.
I forgot that. Yeah.
Okay.
You have this here, and because the flow is going, so we are finding the temperature variation with the
Along the y direction.
direction, right?
Yes.
And what do you mean by there is no variation? Like it's only 1 degree variation. That's what I didn't understand. Because there must.
The maximum minus minimum, if you see, the minimum temperature is 300 and the maximum is 301.
Yeah.
So it is not that significant, right? This.
Yeah, it is not.
Yeah, that is
I was
usually
just
the case.
wondering why- Yeah, I was just wondering why is that?
Usually this term gets significant only when you have very high speed flows. That is only when you have the velocity gradients to be significantly higher. Your source term has a du dy term, del u del y term.
So what you mean is the variation from, like, you have this parabolic profile, right? So that is pretty good variation, right?
Del u del y depends on the actual velocity also, right? Del u del y depends on
Yeah.
your mean velocity, or say like it roughly depends on your
Yeah.
average velocity.
This is parabolic profile, but the rate is not so much. That's what you're trying to say.
Exactly. So only when you
Right.
consider
Also-
very high flows, but the problem is if you consider high flows, the high speed flows, it will be compressible and these equations are not valid. We derived it
Okay,
for
I
an
mean-
incompressible case.
Yes, yes, yes. So also I think there is no variation. I mean, but that will become a time-dependent problem because this is study problem. If you have flow going like in y direction, like say that the flow is going like this, from the bottom it is coming.
Okay,
Say that this is
some mushroom kind
circulating
of,
flow.
okay.
This circulating flow, but even that, but if it is study problem,
Okay. You are saying it's a circulating and a study problem, okay.
no. But wait, that's what I'm trying to understand. So if
Okay.
so what is the problem you solve? We solve for like study problem, is it?
Yes. It's a
But
study
yet
problem.
with
There is
study-
no circulation, right? You have a parabolic profile.
There is no. What I'm trying to ask is, say that there's a constant temperature here. So you say the variation only 1 degree, but there's a constant heat addition. Eventually, the full flow has to reach the same temperature, right? Am I wrong?
Okay, so you are saying as a function of x, if you go along, after some
No,
infinite
as a function
distance.
of time, as a function of time, the same line you take variation as a function of time. But there is no. That's what I'm trying to understand. So there is constant heat being added on top or on bottom. So the temperature
Why do you
has
say
to-
it's not a uniform heat flux boundary condition, right? You kept the temperature as constant. It can be heat addition or removal. It can be either of them. The temperature is constant.
But the temperature of the fluid is zero. That's why I'm assuming heat being added for some time till it
Oh,
achieves
okay.
constant heat.
Okay.
Okay, so I'm just asking, like, since the
Oh,
temperature
okay.
is
So you are
constant-
saying eventually it will reach a case where you have just a conduction profile.
as the boundary, right? It has to. I'm just wondering why it is.
Exactly.
Are we not-
Okay, we'll come to that. We'll come to that. So that is where you
I
have
think
a thermally fully developed flow.
Oh, since we're not considering dou t by dou
Dou
t,
x. I am not considering del t by del x. I've neglected that. Yeah. Actually, there
Del
will
t
be a
by-
variation del t by del x term. There is a del t by del x term that I have neglected in the convection equation. So the first part of the equation, you have a unstudied term and a convection term, right?
Huh.
There you have del t del x and del t del y. I've kind of neglected both of them, saying that convection advection effects are negligent. But actually, your del t del x is also not zero. That is also some finite volume, that has a finite value, and because of that is what the effect you are saying will come into picture.
No, but del t del x is variation in x direction. No.
That is exactly
Okay.
what will happen because it is varying along x. I mean, that is your material derivative. It is part of the material derivative, right?
Okay.
So if you take temperature purely function of time, it is essentially because of the del t del x term is what your temperature will finally reach to that whatever value you
No.
are saying.
No, but so my question, I'll make it maybe much simpler.
Okay.
We're out of time, but I'll try to make it faster.
Okay.
You just forget there's no movement of fluid. It's constant heat.
Okay.
No. You take a line.
Then it will be pure conduction.
Right? Pure conduction. Like whatever we have discussed today, I think this pure conduction equation, dou square u by dou y square
Yes.
t is pure
Equal to
conduction,
zero.
Right? So if, say it's 300 degrees, 0 degrees in the bottom. So eventually it has
Zero-
to, the line.
Okay, 300 on the top, 0 on the bottom. If it is 0, it will be a slope. I mean, it is a slanted line with that slope, 300.
So now it's adiabatic, right? Adiabatic
It's
is like-
adiabatic, yes.
Or like say the fluid is zero initially temperature. So slowly the heat has to flow and it has to become, the temperature has to increase, right?
Yes, temperature will keep on increasing towards your adiabatic end, and near the wall it will be flat because it is adiabatic. It shouldn't have any slope as a function of y, right? So it will keep on increasing, and near the adiabatic wall it will flatten out because delta del y equal to 0. That is what you will get if you do not have any flow. Like even that should be the case. As your flow speed increases, this curvature is what will kind of shift. So your maximum temperature will be much higher somewhere in between. Like it will be even higher. Like minimum max, the difference between the maximum and minimum temperature will keep on increasing as your flow velocity will increase.
Okay. Anyways, yeah, I got it. Yeah.
You got
Something
it.
to look at. I need to do some research. Thank
Okay,
you.
maybe you can go through, or actually, if time permits, maybe we'll take up the 2D problem to solve it in like both in x and y directions. Then maybe it makes more sense. Don't take time will be sufficient. Okay, so and this is our original problem. This is a variant diffusion coefficient. So where you have your gamma as a function of x. So 1 plus 2x plus 3x square. So if you just take that into equation, the only difference again you will be getting here is in your coefficients, where all your coefficients will be a function of x. So now you need to update your AW, A east and AW and A east as functions of gamma, as functions of x, which are so for the left coefficient for a given cell. So it will be it's like if the cell centroid is 0, so you have a gamma of 0. That will be your left face or west face. East face it will be I plus 1. So it's essentially delta x from the west face. So you update these coefficients and the remaining algorithm is same. So just use the same Gauss-Seidel method and then you come up with some. So this is how it's like if I increase the number of grid points from 10, 20 and 40, this is where the solution is kind of converging. So it's from the boundary conditions are like on the left face, on the west side I have taken 100 and on the right side I have taken 40. So this should be fairly straightforward again. The problem again here is if you consider like I already know function gamma as a function of x, but say you have two distinct materials and with an interface in between them. So in such cases your meshing has to be taken appropriately to take into account, say if your mesh falls in between or at the interface. So how do you consider your gamma and all of that? So maybe I think it's almost time. So we will take up that problem next week. Yeah.
You have this boundary in between, right? Like
interface in between.
Yeah, and I mean, kind of boundary. You know the value at that point. You have some condition.
We have some condition, exactly. It's an interface. We have a condition there. We just have a condition that flux should be same.
Boundary like in previous problem, like 2 by 2 y equal to 0 or some kind of condition. The kind of boundary in between, and you have to adjust your Gauss-Seidel matrix, everything regarding that.
No, we don't have to adjust our Gauss-Seidel. We will do it in a different way. We will stick with the same Gauss-Seidel, but we'll use it differently. Maybe that will be discussed in the professor lectures or like in the lecture videos as well. Okay. Okay.
How many problems are left, by the way?
No, this is the last one.
Okay.
So if you have any other questions, we can discuss. Maybe we have like 10 minutes. So this is the last question. So if you have any other questions, we can discuss. We have like 7 minutes.
Nice. Yeah, so it's really nice. Thank you for the walkthrough. It was really great. So I was just wondering, please make this. I've just checked the website. I can see it in the bottom. We have this. You're sharing this doc sheet.
Yes.
Google Sheet. Maybe then you can update the link with some. Maybe put somewhere and you can just share that link.
No, the link is already there in the sheet. It's the same folder. I'll be uploading week-wise.
Where would you put the code, by the way? How would you
in
share
the folder? In the folder. If you click on that Google Drive link, I mean there is a YouTube one and there is a presentation. There is a column for presentation. Okay. So if you click on that link, it will give you some folder. So I'll update in that folder. Like I'll keep a folder week 3 and then upload the course there.
Yeah, that's good. So this is very clear for me. Whatever it is, maybe I will discuss something more regarding whatever we discussed today. So when you said that, we said we will do a 2D diffusion equation. That's what you said. And also you said that this is an extension of discussion. It's very clear for me whatever we have did till now. And also you said that we will have this variation of gamma with a variation of diffusion coefficient with that's what we discussed at the end, right?
Oh, that is essentially you have two different materials.
Exactly. We have this varying diffusion problem. That's one thing we discussed.
Oh, okay.
Also, we'll discuss this 2D diffusion problem sometime, and we can look into it more.
Okay.
Just asking I'm not sure. I'm just asking that in the 2D problem, is your diffusion coefficient anisotropic?
Yeah, you can make it anisotropic. It's up to you.
how difficult is it to model if it is anisotropic?
It is
Is it,
not.
is
It's the
it,
same. It's the same. It is not difficult.
is it straight? Have you done it any time before?
Yeah, I've done for a 2D anisotropic. It will be straightforward. It's just the problem
Because it
is
is-
if the anisotropy extent is too high, that is where your problems comes up.
What do you mean by extent?
So if you have in a 2D problem, if you have kx and ky, like if your thermal conductivity is kx and ky, kx by ky is of the order of 100 or 1000 or something like that.
Ah, okay.
Say if that is the case, then your temperature gradients will be also like along x and y you cannot take the same grid points. So
Yeah, that is okay.
that
No,
is
I
the
was
only
asking this
problem.
because
Otherwise, there wouldn't be any problem in the implementation.
Okay.
It will be straightforward.
I think that will be nice. So is this what we like? Is this what we mainly focus throughout our course? This diffusion equation and going for 2D, going for 3D. Is that what we discuss, or what else do we
Diffusion
actually touch on?
after diffusion equations, we'll go to convection diffusion equations. So the first
Okay,
part
I
is
have-
essentially focused on diffusion.
Yeah, I have seen the lectures. Like I have gone through it. Like he's discussing diffusion for like long time, like 2D goes to 3D. At the end, it's just only like 1 week or 2 weeks where he discusses the CFD main equations, like simple and that stuff was only discussed for a couple of weeks. Until then, he only discusses mostly about this basic
Okay.
equation, and he goes through that. That's
Okay,
what I remember.
okay, I am not aware of the weekly times, but I think there is a significant portion for convection diffusion part.
Yes, it is. But then once this convection is done, is going for 2D, 3D, then going for convection.
And then you have unstructured meshes also.
Oh yeah, that's what. So he only sticks with convection, but he covers all this other stuff. Finally
Yes.
goes to the main CFD.
Yeah, he
simple
already
thing.
provided codes for this. I mean, it's not like it's more about the method. So if you know the method, it should be fairly straightforward to apply even in your fluid case.
No, I'm not saying you should. I'm just discussing the course.
Yeah, sure.
But why I asked you about this diffusion thing is, it is not straightforward if you want to do this anisotropic diffusion with some,
Maybe
other
we'll take up
numerical
one
thing.
example next week.
We should. We
Yeah.
definitely should.
Maybe I'll take an example of an axisymmetric case.
Next week, maybe you can take some time because it is 2D then. Yeah,
2D
whenever it
is
is.
started in the week 4 lectures, right? You have an assignment
Yeah.
also coming up that
It
is on
was-
2D.
It was just released yesterday. Week 4 was released yesterday.
That's what. So by next week you should be going through that, I guess.
Yeah.
So maybe okay. If
Of course.
not, we'll take by next to next week.
So also, can you please share these questions maybe a day before, if you can? Assignment, whatever you are going to discuss.
Okay, these questions. Okay.
Maybe
I'll upload in the
you-
same drive link.
If you can make an announcement, that would be great. Just
I'm
tomorrow
actually
assign-
not there to announce, so I have to
Okay.
it will be from the NPTEL. So I'll just
So
upload in the
reminder-
drive folder, so you can just go through the folder. Like you can keep
If
your
you have
reminders.
it ready for next week now, please put it now so that after looking at the lectures, I will look at the assignment as well. I will be prepared for this as well because it is too forward. It's good, but maybe it is good to practice before, if you can.
Okay, I have not done as of. Okay, I'll prepare and I'll share with you in
No,
the
you
drives
have
in the
to.
same drive.
You have
Yeah.
to. You don't have to. If you have it ready now, please do it. Else, just maybe one day before, maybe on Friday.
Yeah, sure. Maybe on Friday I can
morning
share with you.
Put it. I can just have a look and maybe I can prepare for this as well.
Okay.
It is nice that we can.
Okay, sure.
Okay, thank you. No questions from me.
Okay. Anyone else have anything to say or comment on something? Yeah, if that's it, then I think we are good to conclude. Okay.
Oh, yeah.
Yeah.
Okay, thank you. See you next week.
Yep. Thank you all. Yeah, you can just leave. Yeah. Thank you.